Okay, students, let's go ahead and do our lecture for Chapter 2. Just hit some of the highlights. All right, now, when we were looking at how we describe motion, if you remember from Chapter 1, we talked about using a coordinate system, a line, a number line, to describe motion in one dimension. Well, in actuality, we actually need to go a little bit further than that, because we need to start familiarizing ourselves with what we call the Cartesian coordinate system, which involves x and y axes, okay? And of course, they tell you here that to analyze horizontal motion on a ramp, you always look at positive to the right in the positive x, negative x to the left, and the same thing with vertical motion. Positive y is up and negative y is down, okay? Now, if we look at this and we take this number line and then we put it onto a graph, notice how the line is not a straight line, and that is okay. When we describe motion, it's not always constant. The speed is not always constant. The velocity isn't. So it can be a line that's not a straight line. So when we start analyzing each dot, we see that the dots tells us the position of the person or the object at a given time interval, okay? And so you can see at time 4 we're at 200 meters. At time looks like about time 9 seconds we're at about 550 meters or thereabouts, okay? And so graphs become extremely useful to describe motion of an object, okay? And so that's why we use them. Now, what does a graph tell us? Well, you can hopefully you understand from when you took algebra that anytime you have a steep line, that means that something is speeding up. In other words, the rate of change in the y is much greater than the rate of change in the x. Therefore, that tells us something is increasing at a pretty good rate. Now, whatever that may be, it could be motion, it could be acceleration, it could be, it doesn't have to be motion. When we're looking at a graph, it could be anything. You can graph anything. But anytime that line becomes very steep, that means that that the rate of change is occurring over a very short time interval, okay? If you have a flatter line, then the rate of change is over a longer time interval, okay? In other words, it's not quite as much. So how can we then determine, for example, if we take this straight line segment right here, how can we find the change in position based on this straight line? How can we find that? Well, we can do it a couple of different ways. The easiest way is to take the slope of that line. Take a set of x and y points here and a set of x and y points there, and do the slope calculation, and we can find the value of the object speed anywhere on this line. Now you say, will it be the same at any point along this line? Well, yes, because it is a straight line, okay? So anytime you have a straight line, that tells us that the rate of change is constant, okay, as you move along that straight line. That means it's the same at every point, okay? All right, so hopefully, if you go back to thinking about algebra and when you were doing slopes, hopefully that comes back into play. Now, here's some points to remember when we're looking at graphs. Determine an object's position at time by reading the graph at an instant of time. We call that actually instantaneous velocity when we look at a given instant of time, okay? And of course, when we're looking at the slopes, the steeper the slopes correspond to faster speeds. Again, that's commonsensical if you remember your algebra and your trig when you were doing graphs, okay? And then, of course, we can determine the direction of motion by noting the sign of the slope. If it's positive, that means it's increasing or it's moving to the right. If it's negative, it's moving to the left or up or down, okay? It's according to which axes we're on, okay? Now, can we deduce velocity from versus time graph? Well, we can deduce velocity versus time graph from the position versus time. So, if we take this particular graph, which is position versus time, and then we say, okay, we want to transfer that to a velocity versus time, what will it look like? Well, notice right here, at every point here where the line is nice and straight, that means you have constant velocity. And so if we were to transpose this information from distance versus time to velocity versus time, then notice what happens to our lines. They become flat, don't they? And then it drops down, and then you have a lower constant velocity here, and then it goes back up. You have a higher constant velocity, okay? And so notice the difference in these graphs. Notice how much different they look. Notice how this one looks like kind of a sawtooth, but when you get to the velocity versus time, it's very blocked out, isn't it? It's very squared off, isn't it? Flat lines, and they square off at 90 degrees, right? It comes down here, and then all of a sudden, this, when you go to another time interval where it changes, it drops straight down and then goes flat again, okay? All right, now, what do you think an acceleration versus time would look like? Well, I can tell you what it's going to look like. Acceleration versus time. All right, anytime you have constant velocity, you have zero acceleration. So it's going to be right there. It's going to be zero, okay, at all time intervals. Okay, there's no acceleration, all right? Okay, so here's a quick motion diagram of a car moving along a straight road, okay? Again, velocity versus time. Now notice how the velocity is constant to this point, or excuse me, constantly increasing. It's not constant, it is increasing, okay? Now here's the velocity versus time graph matches this motion diagram, okay? So notice it increases somewhat rapidly, then you get a very rapid increase in velocity. Here it's very high, and then it starts dropping off. So which one would it be? Would it be this one, or would it be this one? Which of these would it be? Which velocity time graph would match the motion of this diagram? Well, notice it's constant, same amount of space covered per time interval, and then you have a sudden increase. So would it be this one right here? Would it be A, or would it be C? Okay, well look, it is C. Okay, now, so when we analyze this motion, now notice this is which velocity versus time, not position. All right, of course none of these are position. Notice how it's constant, and then it really increases. So it's low velocity, then it jumps up to a higher velocity, okay? So those are the ones that would match, all right? Which velocity versus time matches this motion? All right, notice the direction. All right, notice it's going negative. It's going in the opposite direction, okay? So constant, and then you have a sudden increase, but they're all the same. Okay, so which one do you think this one would be? All right. It would be D, because notice it's negative. Okay? You say, how do you know it's negative? Because the final is less than the initial. Okay? All right. Okay, which of the following, looking at position versus time, which of the following velocity graphs matches the position graph? Okay? So notice we've got the change in position is 0. In other words, we stay at the same position during this time interval, and then it does what? It goes down, doesn't it? All right. Well, it would have to be this one, because here we have constant velocity, but it is in the negative direction. So we have 0 velocity right here, 0, and then it does what? Then it drops down and increases. All right, in the negative direction. Okay. Okay. Now let's move on. And you can go back and look at these, okay? Let's look at this one right here. Which velocity versus time graph goes with this position graph? All right, notice how we're increasing position, then it levels off. So notice how the change in position is positively, it's going up, it's increasing. but then the change in position becomes pretty much constant. Okay? Alright, so we're increasing. Which one would it be? It would have to be C, because look, right here, right, pretty much to here we have what? It's constant velocity, but then here it begins to change, begins to decrease, and then it goes to 0 right there. Okay, so boy, these position versus time, comparing it to what the velocity versus time graphs look like, are a little tricky, aren't they? But again, you have to think about what's going on with position. Notice position is constantly increasing. Okay, so that means you've got constant velocity because it's a straight line right there. Then it starts to do what? It starts to slow down. There you go there, and then it goes to 0 right there. Okay, all right, very good. All right, so looking at uniform motion. Now, remember when we talk about uniform motion, that's the same as saying constant motion. Okay, so if we take this position versus time graph, notice that the position, if I were to come along here at any point, not just the ones they mark, but any point, okay, then the change in displacement should be the same at any point, any time interval, okay? Why? Because it's a straight line, okay? It's not a flat line or a horizontal line, it's a straight line, okay? Notice that's why they call it a straight line. So, how do we find this? Well, we just take the slope of the line, don't we? We could take this point and we could take this point and find the slope of the line, and it would be equal at any point along that line, okay? All right, so when we look at a velocity graph and we want to determine the change in velocity, then we can take a displacement graph, and notice the displacement, the change in displacement divided by the change in time gives us velocity in the x direction, okay? Now notice they tell you rise over run. That's some algebraic terminology, but it really is. It's rise over run. Okay. Notice we can break it down this way because remember, what does delta x mean? It means change in. Okay. So x final minus x initial, and it's always x final minus x initial. Okay. Always. Same thing with delta t, t final minus t initial. All right. Okay. Now we can take this equation then and take. Let's look at it this way. Let me erase this. I'm on a different computer, y'all, so bear with me, okay? If we take velocity and we say, all right, x final minus x initial over delta t, and let's solve for x final. Well, notice what the equation becomes. It becomes what? It becomes x initial plus v in the x direction, delta t. Alright, there's our first what we call kinematic equation. Okay, so this becomes a very useful equation if we know the initial displacement, initial x, and we want to find final x. Well, guess what? If we know the velocity times the time, what is velocity times time? Well, when you multiply meter per second times a second, look what happens. It becomes a meter, doesn't it? Well, that's displacement, okay? So we can find the final position if we know the initial position and the velocity and the time interval, okay? Now, we can take this equation, solve for delta. We can take this equation right here, solve for delta x, and we get that equation, okay? So we can create this equation right here from taking what? Right here, okay, and then we can solve for the change in position by solving for delta x right there, okay. All right, okay, some proportionality relationships here. They're just going over just some it actually goes back to your algebra rules when you looked at straight line graphs and what we mean by proportional. If we look at proportional, what does that mean? Well, they were talking about proportionality here. X is proportional to the time interval. Well, all right, what does that mean? That means the greater the time interval, the greater the change in x. Okay. All right, now Let's move on. You can read that. That's in your text. All right, here is a position graph of an object. At time 1.5 seconds, the object's velocity is what? Okay, well, let's read it. Well, here's 1.5. All right, go up and read it right here. So it's going to be about what? Let's see. Let's see. I did read that right. At 1.5, the object's velocity is what? Well, here's 10. It looks like it's going to be around 15, right? No, that is not right. Okay, that is a typo error because look, at time 1.5 seconds, I am reading it right? Yeah, 1.5, it's not 20. Okay, so that's wrong. Okay, that's an error. Okay. Alright, displacement versus time. When we look at delta x is equal to the area of the velocity graph during the time interval. You say, well, now how do we get that? Well, it's very simple to understand. Look, if we take a flat line, if we have constant velocity, okay, and let's say this is velocity versus time graph, and it's flat. All right, let's do this right here. What do we got? Well, we got a square, don't we, or a rectangle. Well, what is the area of a rectangle? Well, it's the length times the width. Well, what is the length? Well, the length is time. What is the width? It is the velocity. So when we multiply velocity times time, what do we get? We get x, displacement, okay? And that's what they mean by that, okay? So it becomes very easy to determine the displacement if all you have is velocity versus time. If you have constant velocity, well, hey, just go from whatever time intervals you're wanting to look at and then say, okay, we're going to go from here to 1 to 3. Well, that's a difference of 2, isn't it? So 2 times 12, well, okay, 2 times 12 is what? 24 meters, isn't it? So the object travels 24 meters during that 2-second time interval at 12 meters per second, okay? It's real easy to calculate. Okay, here's another velocity graph, an object that is at the origin. At time 4 seconds, the object's position is what? Okay, well, when we come out here to 4, all right, well, look, we can do two graphs. All right, we do right here. All right, so we got 2 times 4. So 2 times 4 is what? 8. And then we have from 2 more seconds, but notice that's a right triangle, okay? That is a right triangle. But notice which way the graph is going, okay? Notice that the velocity is decreasing, okay? But it's still in the positive direction, okay? It's still in positive, the positive direction on the graph. All right, so what is the area of a right triangle? Well, it's 1/2 the base times the height. The base is 2 seconds, and the height is what? 4, isn't it? So we get basically so that's going to be equal to 4, so that's equal to what? 8 plus 4 is equal to what? 12? 12 meters, is that right? Okay. And that's exactly right, 12 meters. We take the area of this rectangle and then take the area of the triangle, and it's 1/2 the base times the height because it's a right triangle. Add the two together, boom, you get it, okay? All right, now, so that's one way of determining an object's displacement from a velocity graph. All right, what about instantaneous velocity? All right, now we're looking at, we're on page, in our text, page 36. Now, there's a little bit, instantaneous velocity is not necessarily always the constant velocity, okay? So please remember that. Instantaneous velocity is not always the same as the average velocity, or that's what I meant to say, not constant, but average velocity. So average and instantaneous are not always the same. However, they can be, okay? If you have, for example, if you look at this section of the graph right here, actually, let me do this. Actually, sorry. Oh, what am I doing? There we go. Actually, if we look right here, we look up here in this region of the graph where it's pretty straight, where it's pretty, it's pretty straight, we would find that the instantaneous velocity and the average velocity in that section of the graph would be the same. But when we start getting down here where it's curved, then the average velocity and the instantaneous velocity are not going to be the same, okay? Because it's a curve, all right? Now, so what do we mean by instantaneous velocity? Well, it's actually the first order derivative of the displacement function, okay? So But since we're not doing derivatives, we'll look at it a little differently, okay? What do we mean by instantaneous? Well, it is the displacement, or the velocity at any given moment. For example, if I were to look right here at this dot and say, all right, what would be the instantaneous velocity at time? Oh, that looks like what? 0.5, that's 1. What's that going to be close to? Like 0.75 seconds maybe, approximately, somewhere around there. Okay, so that would be 0.5 seconds, wouldn't it? All right. Well, how can I find that? How can I find what the instantaneous velocity is? Well, we can take the tangent of that line right there. We could take the tangent of that point right there. We could, which is basically saying what? The slope. We could take the slope of that line. And so what we could do then is we could come in here and draw a nice, perfectly straight line through that point at that given time interval and take the slope of that line and come down here and say, okay, what's x and y here and what's x and y there, and take the slope of it, and that would be the instantaneous velocity for that given point. And then we could move on up. We could move on up then and go to another point and say, okay, what's the instantaneous velocity at 1 second? Well, here again, we're going to take the line passing through there, passing through that point, take the slope of that line, and we could find it for that point, and so on, okay? So please understand that the instantaneous velocity and the average velocity are not always going to be the same, okay? Okay. All right, and basically what I just said there, okay? All right, take the slope of the line, all right? Okay, and you can look at this and again, what I just said, taking the slope of the line, and again, I don't want to keep rehashing that, okay? Now, what about one that's curved? Well, it becomes a little bit more complicated, doesn't it? Well, not really. If we want to know what it is, just do the same thing right here, okay? All right, let's move on. We beat the fire out of that, okay? Now let's look at acceleration. All right, so how do we define velocity by doing what? We said that velocity is the rate of change in position of an object with respect to its direction, right? Well, guess what? Acceleration is the rate of change in velocity with respect to position. And by the way, these are vector quantities. Velocity is a vector quantity. Acceleration is a vector quantity. These are all vector quantities, meaning what? That it has magnitude and direction. Now, how do we find then it says the ratio of velocity versus time is the slope of the velocity versus time graph. Well, no duh. Okay. And of course the ratio of that is the rate of change of velocity, which is acceleration. Okay. Now don't forget, we can say v final minus v initial, watch now, over the change in time. And notice what our equation could become. If we wanted to find the final velocity, well, okay, let's rewrite it here. Final velocity would be what? The initial velocity plus the acceleration times the change in time. So there's another equation. We could find the final velocity if we knew the initial velocity, we knew the acceleration, and we knew the time interval. Okay? So that becomes very useful, doesn't it? And likewise, we could turn around and solve it for initial velocity. If we didn't know the final velocity, but we knew the initial velocity, and we knew the acceleration, and we knew the time interval, then we could turn right around and solve the equation for initial velocity. Okay? Do I need to write all these equations? I mean, come on, you should be good enough in algebra to solve that for VI. Okay? Okay. Okay, units for acceleration. Now, just like the units for velocity, the units for velocity are what? Units for velocity is meters per second, right? Meters per second. The units for acceleration then becomes what? Well, it changes, doesn't it? We use, since it is the change in velocity per given time interval, then the units for acceleration become what? Meters per second, right here, or meters per second squared. And so notice that it is a unit of velocity, but it's a unit of velocity divided by a time interval. So you can write it this way. Oh, you can write it this way. All right. Meters per second or meters per second squared, which is actually it's more commonly written that way now, okay, to write it meters per second squared, okay. All right, now they give us an example here of how to find the line accelerates from what? Now I'm changing its speed by 9.5 meters per second for only 1 second. Okay, now that's another thing too. I'm glad I'm reading this. Look right here. When you look at that right there, what does what does this mean? Whenever you see an acceleration, that means what? Notice it's meters per second squared. So what does that mean? That means for every 1 second time interval, the object is increasing in velocity by a value of 9.5 meters per second. Okay? All right, y'all, I got to pause just for a second. If I can figure out how to end. That's not how I wanted to end. Here we go. Okay, sorry for the interruption, but as I was saying, when we look at acceleration, all right, for example, 9.5 meters per second squared. What does this tell us? That tells us that it's changing its speed by 9.5 meters for every second, okay? All right, now let's move on. Okay, this is just showing some different graphs and what they look like of the particular object in question. And again, you can go back and look at these, all right? Okay, now, sign of the acceleration. When we look at velocity versus time graphs, and we see the line go downward this way or even underneath, notice that it tells you that the slope is negative. The slope is negative. Now, what does that typically mean? That means that the object is actually slowing down, right? It's slowing down here. However, right here, it's going from low velocity to higher velocity, so it's actually speeding up. But you still get a negative slope. Okay, why? Because the final velocity here is greater than the initial velocity. It's just in the negative quadrant. Here the final velocity is less than the initial velocity. Okay, so here it's negative because why? Because it's decreasing in velocity, but here it's negative because we are the quadrant we're in is negative. We are in the, notice, let me erase this. Notice right here, this is the negative portion of the y-axis, okay? Okay, so please pay close attention to that. If you're looking at a graph and the slope is in the positive quadrant as opposed to the positive x and y, or in the positive x, negative y. Pay close attention to that. Now, let me say something else too. Just because an object has negative acceleration does not mean it's not moving in the positive x direction. Okay? You can have an object that is moving in the positive x direction but is slowing down. Therefore, it will have negative acceleration, but it's still going in the positive x direction. So you got to be careful of that, okay, when you're looking at acceleration. All right, let's move on. And again, you can go back and look over these. These are good examples, but y'all, we're not going to go over every single example, okay? I just want to hit the highlights with you, if I could ever get to it. And actually, there's too much overkill in these slides, okay? I may just start doing my own slides, okay? Because there's way too much overkill. That's what I'm wanting to get to right there. All right, now constant acceleration. Well, what does that mean? Well, anytime you have constant acceleration means what? Now, I didn't say constant velocity. I said constant acceleration. That means that the velocity is changing at a constant rate for each time interval, okay? That being the case, you have constant acceleration. For example, gravity. If you take an object and you push it off of a table or a hill, let's just say a boulder, okay, it will accelerate downward at a constant rate of 9.8 meters per second squared, and that is negative, by the way. What does that mean? That means for every time interval, its velocity is changing by a value of 9.8 meters per second. So what does that mean in the end? That means my final velocity is going to be a whole lot greater than my initial velocity. That's why, if, someone's standing on a ladder and they drop, let's say, a quarter and it hits you in the top of the head, well, you feel it, but it's not all that bad. But if they're standing on top of a building and it hits you in the top of the head, it's going to feel a little bit worse, okay? So, and the reason being because it fell through a greater distance, a longer time interval, okay? All right, so constant acceleration. Now, again, notice how we calculate it the same way, use the same equation. Here's this equation I showed you earlier, where we derived it from this equation, the final velocity. If you know the initial velocity, then you can, and the acceleration of the time interval, then you can find the final velocity. Okay? Sometimes initial velocity can be 0. All right, it can be 0. All right, now, okay, moving along. Now, here's another equation, and I think what I'm going to do, and they go through these slides how you can derive these equations, these kinematic equations from graphically, and you can also do it by integration. I think what I'm going to do is I actually have this written up, handwritten, and instead of me trying to go through every one of these and derive it graphically and taking about 30 minutes of lecture time, I'm just going to email it to you, how it's derived. Now, do we have to know how it's derived? No, you don't have to. But it's just kind of interesting to see how graphically we derive these kinematic equations, okay? So here's another kinematic equation. And we can also find final displacement from initial displacement, changing velocity, initial velocity, the changing time interval, and the acceleration. Now, where does the 1/2 come in? Well, it comes from this area right here. All right, right there, the area of a right triangle is what? Well, the area of a right triangle is 1/2 the base times the height, right? Okay, well, the height is what? Well, the height is the acceleration times the time, right? All right, so we got initial velocity here, the base, the height, acceleration times time, okay? And notice it's times time squared, okay? It's time squared. All right, now, okay. And then we have one more equation, kinematic equation, and this is probably a very, very useful one too. You use this one a lot, and you also use this one a lot, but you can use them all right? So we have the V final. V final is equal to what? V initial plus AT, change in time. V final is equal to V initial plus acceleration times delta t. Then we have X final is equal to X initial plus initial velocity times change in time plus 1/2 AT squared. And then we have this equation, okay? We have velocity final squared is equal to velocity initial squared times 2A delta X, okay? Another very useful equation. Notice this one does not have time in it. You say, well, how do we get to this equation, okay, well, we take this equation right here and we substitute, we solve for time. In other words, we take time out of it, okay? And so if you take this equation right here and solve for delta t and then substitute in wherever there's a t, and by the way, it's supposed to be a delta, it's gone. It's gone, all right? Okay. Okay. So here's our equations for what we call our kinematics. These are called kinematic equations. Okay. For constant acceleration. All right. Here's one we've already looked at. We've already looked at that one. We've already looked at this one. Okay. We can actually add some more. Okay. All right. Now let's go to. Okay. Here they give you an example. And again, don't forget the study area. The study area of the MyLab and Mastering Physics is a good place to go and watch short little tutorial videos too. They do a lot of these samples in there, okay? Alright, I want to end and go to free fall. If I could move the thing right. There we go. Free fall. I want to finish this lecture up. Okay, so free fall. Alright, so what does it actually mean? Any two objects in free fall, regardless of their mass, have the same acceleration. Simply put, so when an object is falling, regardless of its mass, and you say, well, I just don't believe that. Well, Galileo proved it. He's the first one to propose it. Newton came along and built off of Galileo and built his laws of motion. But you can actually take a piece of paper, wad that paper up. If you take a sheet of paper and a rock and drop them at the same time from the same height, well, of course, they're not going to fall at the same rate. Because why? Because the surface area of the paper produces a lot of air resistance. But if you wad that paper up into a ball and then take a rock and drop them from the same height and release them at the same time, believe it or not, they will hit the ground at the same instant, okay? Verifying free fall. And so objects do fall with a rate of, notice right here, and whoa, I did not mean to do that. Notice that it is negative 9.8 meters per second squared. Why is it negative? Because the starting point is 0, okay? And so as the object is falling, it's falling towards the earth, the surface of the earth, okay? So therefore its displacement and its velocity is in the negative direction. Now, you say, well, Ms. Shields, can we? Yeah, and you'll see me when I work some of these problems. We will. There are places where, you know, again, the math never lies. The mathematics will remove the negative, but then there are cases to where we say, okay, the object's going up. We know gravity's negative, but we want to know how high above the surface, so we just make everything positive, and it makes things a whole lot easier, okay? And you'll learn how to work that. Now, notice here they don't show you it negative, but they do tell you it is downward, okay? So they do tell you that. So in a sense, it's in the negative direction is the way to think about it, okay? Okay, and we call that free fall, okay? Notice there will never be a problem that uses a negative value for g. All right, by definition, it's always positive. Well, that's not always the case, okay? Because when you do a quadratic equation, if you're solving for time, then guess what? Well, you got to remember that g is negative, okay? All right, so I kind of disagree with what the authors say here. Because free fall motion with constant acceleration, we use the kinematic equation for constant acceleration. A and the y is negative g, okay? Okay, all right. So, again, let's not get too hung up on that, all right? All right, now, these are good samples, too, we can go through, okay? All right, I think that's all we wanted to cover. That's where I want to stop, okay?